I hope you have tried a few problems from tutorial sheet 2. Essentially, they are on Lebesgue measure and Lebesgue measurability. Have you tried a few problems? Yes or no?
Yes, sir.
Yes, sir.
You are able to approach it, some ideas, if not the final solution. Problems are not hard. There is no point in giving too much hard problems. But what I felt is that the ideas supplied in the lectures should be clear and you should be able to apply those ideas. That's it. Okay, so let us quickly discuss a few problems from tutorial sheet 2. I don't know whether I have done the first problem in the last lecture, but I told you the basic idea and why that problem is important. As you all know, Lebesgue countermeasure, the basic idea is to approximate measure of a non-standard object with the help of a standard object, namely open set. So instead of measuring a given set, we measure an open set containing the given set. That means we do an overestimate and then try to get better and better overestimates. That's what we are doing by taking infimum. Okay. And this problem essentially says that given any set E, you can always find an open set containing it such that the measure of this overestimated thing, measure of G epsilon, is less than or equal to measure of E plus epsilon. Assuming measures are finite and so on, if you allow me to transpose to the other side, it gives me m star of G epsilon minus m star of E is less than epsilon. That means roughly the measure of this annulus E is given set. You are enclosing it with a larger set, namely G epsilon, which is open. So the difference between E and G epsilon is that annulus, and that annulus has measure less than epsilon. Okay. But I cannot say this very precisely because m star of E can be infinity. In that case, transposing to the other side, etc., makes no sense. Okay. But if you are in the finite measure setting, then what it tells is that the outer measure of the overestimate minus outer measure of the thing that you want to find measure is less than epsilon. So the measure of the object that you want to measure can be well approximated by measure of an open set. This is what it tells roughly. Now, whenever you get some inequality involving epsilon and so on, the first thing that it should come to your mind is that m star is basically an infimum. That means it is a greatest lower bound. Therefore, anything greater than it cannot be a lower bound. Okay, so that's the idea. Recall that m star of E by definition is infimum summation L of In. E is contained in union in In. Instead of covering with open set, it is enough to cover with open intervals because every open set is countable union of open intervals where INs are open interval. This is how we took our definition. So basically it is an infimum or greatest lower bound. So given epsilon greater than 0, m star plus epsilon cannot be a lower bound. For that set. I don't want to repeat it, so I will write for the set above. That means, that is, there exists a countable sequence, a countable family of open intervals Jn such that E is contained in union n Jn and summation length of Jn is less than or equal to m star of E plus epsilon. You can find an element in the set which is strictly less than the greatest lower bound plus an epsilon, because greatest lower bound plus epsilon is not a lower bound. But here why we are putting less than or equal to is m star of E can be infinity, length of Jn's can be infinity, and so on. So in order to cover that case as well, we put equality here. Is it clear? So this is just by applying the infimum idea. Okay. What you want? You want an open set. You already have open intervals, have Jn. Okay. So take union. Let G epsilon is equal to union n Jn. Then it is clear that G epsilon is open, which is open, being union of open sets. And E is contained in G epsilon. What more we want? M star of G epsilon should be less than or equal to M star of E plus epsilon. Okay. M star of G epsilon is same as M star of union I n Jn. By countable subadditivity, this is summation n M star of Jn. Jn being interval, it is summation n L of Jn. And summation n L of Jn by the choice is less than or equal to M star of E plus epsilon. So any given set roughly can be, what it tells is roughly is any given set can be, outer measure of any given set can be approximated by outer measure of an suitable open sets. And the error can be made less than any arbitrary number. Okay. Second one is follow-up of the first one. Now, instead of finding an open set, you are supposed to find a G delta set. Okay. And if you allow me to take G delta set, in fact, you can match the measure. If you take the open set, the difference between the measure is less than epsilon, roughly. And here what you can do is you can find a G delta set that such that the measure is exactly the same. Outer measure is exactly the same. We will prove all these things once again in the class when we talk about regularity theorems, and but in the context of measurable sets. These problems we are not assuming E to be measurable. Okay, can somebody tell me how to proceed? Open sets you can create. By problem 1, open sets you can create. But now you want G delta set. Yes. Whether somebody could prove it or not. What is G delta by definition?
Union of countable open sets.
countable union of open set. That's the better way to say. Yeah. So you treat open sets as the starting point and you want to build new sets. Okay? But you know that countable union of open set is open and finite intersection of open set is open. So I cannot take countable union. I don't know what you told. It's not countable union, countable intersection. Okay. Countable intersection of open set is called a G delta set. If I take countable union, again I will get open set only. I want to create something new, possibly something new. Okay. So that I have to take countable intersection. Delta stands for intersection, sigma stands for union. So with that in mind and problem 1, how do I proceed? I can create an open set from problem 1. Given any set, I can create an open set larger than that, such that M star of open set is less than or equal to M star of the given set plus any predetermined tolerance level. So what's the idea?
So for every epsilon, we can find a G epsilon set.
Okay.
And take intersection of all these.
But when you say every epsilon is uncountable in number.
Take a natural number, sir, 1 by n.
So you have from epsilon, you have to go for 1 by n to handle countable case, right? So take epsilon is equal to 1 by n belong to n. From problem 1, there exists an open set. There exists open set G, I will call n, Gn, such that this open set encloses given E is contained in Gn, and outer measure of this overestimate is less than or equal to outer measure of the object you want to measure plus the error level. Error level is 1 by n. Okay. This is what we proved in first one. Now I want to create a G delta set, that is intersection. So take G to be intersection Gn, an element of n. Then by very definition, G is a G delta set because it is countable intersection of open set. G is a G delta set. Okay. What we want, M star of G is equal to N star of E we want. Okay. Now since E is contained in Gn, for all n, E is contained in intersection Gn. Note that E is contained in intersection Gn. That is, E is contained in G. Therefore, one part is clear. M star E less than or equal to M star G is clear from monotonicity. Therefore, M star of E by monotonicity of Lebesgue countermeasure is less than or equal to M star of G. Okay. But M star of G is less than or equal to M star of Gn. Because G is contained in Gn. Again use monotonicity. And M star of Gn is less than or equal to M star of E plus 1 by n. Now forget about M star of Gn. What you have is thus M star of E less than or equal to M star of G less than or equal to M star of E plus 1 by n, and this is true for all n in n. And this should tell you that thus M star of G is equal to M star of E. So given any set E, you could find a G delta set obtained by taking intersection of open set. So G is something like a standard object, such that outer measure of the standard object exactly matches with outer measure of the object E. arbitrary object E. So open sets are like standard object, G delta sets are like standard object, and so on. But starting from open interval, you can go to open sets, then G delta sets. Next problem is interesting. While defining Lebesgue outer measure, we took open intervals in the definition. And this theorem, this problem says that, in fact, you can take any type of intervals, need not be open. It can be open, it can be closed, it's semi-open, semi-closed, or in that collection, one can be open, one can be closed, and so on. Okay. So like that, you can view M star E in different ways. But finally, it will give same M star. Okay. So that is slightly longer to prove because you have to prove several things. So let me fix some notations first. Okay. M star E, you know, by definition is the following. M star E equal to, let E subset of R. M star E is the M star that we have defined. M star of E is equal to infimum of summation L of In, where INs are open intervals. Okay. E is contained in union n In. Each In is an open interval. So this is how we define M star. Now what we do is, instead of taking open intervals, let us take semi-open, closed in the left and open in the right. All intervals are of that kind. Okay. So I will define M star E suffix CO, closed open, is equal to infimum of summation L of In. E is contained in union n In. Each In is of the form closed AN, open DN. Closed from the left and open from the right. Each In. Okay. So again, INs are of same type. Now let us take the third one, that is left open, right close. So that I will write as MOC. And how do I define? Summation length of In. E is contained in union In, and each In is of the form open AN, closed DN. And maybe we can take INs, each In as closed. So that I will write as MC star E. C stands for close. Infimum of summation L of In. E is contained in union In, and each In closed. And in the last, the mixtures are allowed. That is, some In can be open, some Ins may be closed, and so on. So that I will write as M mixture of E is equal to infimum of summation L of In. E is contained in union n In. Ins are interval. That's it. One of the In can be open, IM can be closed. Then if you take some other IR can be open, closed, and so on. Okay, so this is mixed type. And what the problem demands you to prove is that all this quantity will be the same. Once you fix your set E, whether you approach through open intervals, whether you approach through closed intervals, semi-closed, semi-open, whatever it is, okay, claim is this. M star E is equal to M CO star E is equal to M OC star E equal to M C star E, everything closed, and that is same as mixture is allowed. So all these things are same. Okay. For convenience, we took our intervals as open. That's it. So this is how you can fix the notation. Now, this is what we have to prove. This equation, or rather chain of equation, we have to prove. Could somebody do this? And out of that, certain inequality will be easy to prove. Could somebody do it? See, this is a tutorial. Are you expecting me to just go on solving one by one without any interaction, without looking at you? Anyway, you are not switching on the video. That itself is a bit irritating, and there is no point in repeating this fact. If you don't want to show your face, it is okay. I cannot demand it. But you should understand that it is really embarrassing. We are supposed to have physical classes. Somehow the situation demands to adjust with the whatever available to us. But then even if you are not switching on the video, is slightly, I can't see your face, I can't see what you have done, and whenever I ask question, I have to repeat several times whether you could do. Nobody want to voluntarily come and answer. I am not testing your knowledge. Please listen. Please understand. I am not testing your knowledge. I am just trying to interact with you. And if you have something to tell, okay, this is the way I approach, I will be happy to receive it. But in lecture classes, I cannot spend too much time to listen to you. But tutorial is different. Anyway, so I can stop asking question and go on writing and finish this 1 hour. That I can do. So don't think that I am unable to do it. Don't make me to ask ask same question several times. If you don't want to answer, you can tell me now. Either you can come forward, or through your class rep, you can tell that it is our practice not to respond. Then next time onwards, I can keep this in mind, and I don't want to ask any questions. Okay. Could somebody do this problem? This is the last time I want to ask.
Yes, sir.
What is your approach?
I tried writing intervals in the form of other intervals.
And you could succeed to prove that all these 5 quantities are equal?
I tried it for one of them.
So as you did, I will also try with one of them, and maybe similar approach you can do. What I will do is that I will try to prove, for instance, M star E, which was our original definition, to be equal to, let us say, MM star E, mixed. Okay. So mixed seems to be, it involves different types. So let me try to prove. We prove, and you may try to copy the same argument in the other. M star E is equal to MM star E. As I told, in this equation, I think one inequality is trivial. Which inequality is trivial? When I consider M star E, I am taking only covers with the open intervals. Whereas when I consider M star E, I consider covers where intervals can be of any type. Okay. So do you see that one collection is already contained in the other? Which one is contained in which?
Open is contained in the mix.
Yeah. So the collection that we deal in M star E is contained in collection that we deal in MM star E. Therefore, infimum of the larger set is less than infimum of the smaller set, right? It is
Yes,
clear
sir.
that M star E is less than or equal to M star E. Because the collection involved in M star E is of larger type compared to the collection involved in M star E. And you know that infimum of a superset is less than or equal to infimum of the original set. Okay. So only thing is to prove the other way around. To prove that M star E is less than or equal to M star E. It is enough to prove that for any epsilon greater than 0, M star of E is less than or equal to M star E plus epsilon. Okay. It is enough to prove. I will be using infimum idea again. For any epsilon greater than 0, M star of E is less than or equal to star of E plus epsilon. Do you agree?
Yes, sir.
Now, star of E by definition is an infimum. Therefore, star plus E cannot be a lower bound. Okay, apply that. By definition of infimum, there exists, I am considering the definition of star E. Okay, there exists a sequence of intervals in. In can be of mixed type. One in can be open and another in can be closed. Another IR can be open, close, and so on. An element of n. INs of mixed type such that E is contained in union n in and M star E plus epsilon is greater than, because star E is infimum. Okay. Summation, let me write on the other way around. L of in is less than or equal to star E plus epsilon. By the definition of star E, this or the property of infimum, this is true. N equal to 1 to infinity. Now, next what I do is, for each of this interval in, which can be of mixed type, I will try to find intervals which are open. Okay, and whose length distance or the length of that interval and length of the in, that difference is small. Okay. So let us take in, a particular in that collection. I don't know what is its type. It can be something like this, for instance, or it can be of this type, for instance. I don't know, but let me work with the bounded for the time being. Now what I do is, I want to cover this in, or I want to enclose this in with an open interval, let us say in dash. And given this in, I wanted to cover it with some in dash. Such that, okay, consider open interval in dash for each particular in, for open interval in dash, such that in is contained in in dash. That is always possible to get an open interval. Given in, I can find an open interval containing it. Further, what I want is length of this in dash, larger interval, larger open interval, is equal to 1 plus epsilon times length of IN. Length of IN plus epsilon times length of IN. Why this is needed? What is magical about this 1 plus epsilon and so on? You will come to know. Before that, tell me whether this is possible or not. Given an IN, can I find an open interval IN dash such that the length of IN dash is equal to length of IN plus epsilon times length of IN. That is length of IN plus a something small. Is it possible?
Yes, sir.
How do I adjust that? Suppose your IN is say A and BN. Okay. A and BN. Then what you take as IN dash is, can you tell me?
AN minus epsilon.
AN minus some number and BN plus some number. Okay. That AN minus say epsilon 1, BN plus epsilon 2. That epsilon 1 and epsilon 2 you should adjust such that the total distance of total length of IN dash is length of IN plus epsilon times length of IN. Okay, so what should I take? Tell me. Can I take this as AN minus length of IN by 2 and BN plus length of IN by 2? Epsilon times length of IN. Suppose I take like this, then what will be the length of the IN dash? Should I draw once again if it is not clear? This is your IN, suppose. This is AN, BN. This is given IN. Now I want to find an IN dash, okay, which is open. That is always possible. Now I want some relation between length of IN dash and length of IN. What I do is I take this to be AN minus epsilon length of IN, assuming these are all finite, by 2, and this as a BN plus epsilon times length of IN by 2. Okay. I don't know whether this will work. Now suppose I find length of IN dash. What is length of IN dash? Bn minus an, Bn minus an, that is length of IN, plus epsilon times length of IN. Yes, I will get it. So like this, I can always do that. Okay. So I am working with bounded. If it is unbounded, you can think what can happen. So this is always possible. Since E is contained in union and IN, I can cover E with IN dash also. Now, E is contained in union and IN, and this is contained in union and IN dash. Okay. So what I want to prove is this: M star of E less than or equal to MM star of E plus epsilon. Let me start with MM star of E plus epsilon. Okay. You know that MM star of E plus epsilon is greater than or equal to summation length of IN. By applying infimum, we selected IN like that. Okay. And this is IN is contained in IN dash. Okay. And length of IN is 1 plus epsilon, 1 by 1 plus epsilon times length of IN dash. So this can be written as summation n equal to 1 to infinity, 1 plus epsilon power minus 1, 1 by 1 plus epsilon, length of IN dash. This is how I selected IN and IN dash. Okay. So 1 plus epsilon I can pull out from the summation, and summation n is equal to 1 to infinity length of IN dash. Okay. Now as you have seen, E is contained in union IN dash, and IN dashes are open intervals. Okay. So M star of E is, by definition, it is infimum of summation length of IN. So less than or equal to length of IN dash. IN dash are open. And this is less than or equal to 1 plus epsilon times mm star of E plus epsilon from the last from star. From star. That is 1 plus epsilon times mm star E plus epsilon times 1 plus epsilon. Okay. Now remember, epsilon is arbitrary. Epsilon is arbitrary. Therefore, this should give that. Therefore, m star of E, you can adjust your epsilon suitably. Maybe some epsilon dash you have to work, and then epsilon dash you can take as 1 by 1 plus epsilon or whatever. Finally, you will get m star of E is less than or equal to mm star of E. These things can be adjusted again. Okay. And that proves. Already we have the other way around. Mm star of E is less than or equal to m star of E. Okay. Therefore, m star of E is equal to mm star of E. I think my choice, this epsilon times ln plus ln is not a very good choice. If you have adjusted your epsilon dash here properly, here you could have got. This is something like you might have seen this many times. If you started with epsilon by 3, finally you will get epsilon. But if you have started with epsilon, finally you will get 3 less than some 3 epsilon. But that doesn't matter. Epsilon is anyway arbitrary. Okay. So this is that clear what I want to say? In the proofs, in real analysis and so on, sometimes instead of working with epsilon, you may say start with an epsilon by 4, so that finally you will get the required quantity to be less than epsilon. But had you started with epsilon, you will get finally it is less than 4 epsilon. But that doesn't matter because anyway epsilon is arbitrary. Okay. Similarly, so had I started with a suitable thing here, I might have got much more better in appearance. But that doesn't matter because epsilon is arbitrary. So this is small, this is small. So finally you will get m star of E is less than or equal to mm star of E. Okay. Similarly, you try to do for the other. So idea is, given an interval, you try to convert it slowly to open interval. Okay. With that, let me stop that problem. Next one is again interesting. So what you have to do is, it's almost same idea. Instead of taking intervals, open intervals, you can take open intervals with rational endpoints. Keep in mind that rationals are dense in real. Prove that m star of E is equal to infimum summation length of in, infimum taken over script IE, where IE consists of family of IE consists of countable families of open intervals with the rational endpoints. Okay. Original definition was open intervals, but now we are taking open intervals with rational endpoints. Okay, so I would call this as MQ star E, that is better, with rational endpoints. Okay, and M star E for the original definition. Okay. Then one inequality should be trivial. Which inequality should be trivial? Now you have M star E definition. Okay, you know. Now, if you compare MQ star E and M star E, can you say something?
M star E less than equal to M star E.
In M star E, you are considering open intervals with endpoints, no restriction. Whereas in MQ star E, you are considering open intervals with restriction that endpoints should be rationals. Okay, so this is more restricted family. MQ star E, in the definition, you are using restricted family, and in the M star E, you are using a larger family and then taking infimum. So it is like an infimum of a superset. Infimum of a superset is always less than or equal to infimum of the original set. Okay, therefore we have clearly M star of E, in whose definition you have a larger collection, will be less than or equal to MQ star E. So we have to prove the other way around. Okay. For that, it is enough to prove. Let me first write it. To prove MQ star of E is less than or equal to M star E. Again, use epsilon. For this, it is enough to prove that. It is enough to prove that MQ star of E is less than or equal to M star E plus epsilon for any epsilon greater than 0. That's our goal. But if you look at M star E plus epsilon, it is something greater than greatest lower bound. M star E is a greatest lower bound. So M star E plus epsilon cannot be a lower bound. So use that idea. Okay. Since M star E is by definition an infimum, M star of E plus epsilon cannot be a lower bound, and hence there exists In and so on. There exists INs were in the definition of M star E, but in the definition of M star E, we are trying to get open intervals without any restriction on endpoint. There exists INs open interval. E is contained in union IN, and summation length of IN is less than or equal to M star of E plus epsilon. This much you know from the definition of M star E and the property of greatest lower bound. What is IN? INs are open. Endpoints can be rational or real. I don't know. Okay. Now I have to go for the rational. So for that, suppose you have IN is given to be open. You can always find a open interval IN dash with endpoints as rational, and length of IN dash and length of IN, if you compare, the difference is small. Okay, like that I can always find. Now, for each IN, same idea as we used in the previous problem. Each IN, find an open interval IN dash with rational endpoints such that IN is contained in IN dash, and also I will put a restriction on the length, because finally I want to connect everything with the length, such that length of IN dash is less than or equal to 1 plus epsilon times length of IN. Now, is it possible? Let us check. So now this given IN be AB, A and B are real. Okay. Now for real A, can I find a rational whose distance from A is a predetermined number, let us say epsilon 1? Is it possible?
Sorry, sir, repeat.
AB. So this is given to you. This is IN. A and B are real. Now, A is real. What I want to ask is, can you find a rational which is close to A, closeness as a predetermined number epsilon 1? Can I find a rational whose distance from A is less than epsilon 1? Is it possible? Yes,
Yes, sir. Yes,
then
sir.
Yes, sir.
Yes, sir.
right? Then there exists A dash in Q such that modulus of A minus A dash is less than epsilon dash. Okay. And B is in R, then there exists B dash in Q such that modulus of B minus B dash is less than, let us say, epsilon double dash. Whatever epsilon dash and epsilon double dash you are taking. Okay. Now you consider A dash B dash. Sorry. Therefore, A minus epsilon dash, I am just trying to say that this is always possible. Finding an IN dash with this property. Here you will have A dash minus epsilon dash less than A dash plus epsilon dash, I suppose. Okay. Or let me write the other way around, because I don't know epsilon is rational or not. Okay. So what I do is A minus epsilon dash less than A dash less than A plus epsilon dash. It is possible. And similarly, B minus epsilon double dash less than B dash. I can find a rational number A dash and B dash like this. B plus epsilon double dash. Okay. Now let me just check what I have done. Therefore, length of A dash B dash interval. Length of A dash B dash interval is B dash minus A dash, which is less than or equal to B plus epsilon double dash minus A B dash. I am replacing by B plus epsilon dash, and A dash is greater than A minus epsilon. So minus A dash will be less than minus A plus epsilon dash. Okay. So this is equal to B minus A plus epsilon dash plus epsilon double dash. And this is length of interval AB plus epsilon dash plus epsilon double dash. For any predetermined epsilon dash and epsilon double dash, I can do this. Okay. So this is my IN, length of IN. Plus epsilon dash plus epsilon double dash. Okay. So this is how I did it. Length of IN dash. So what I claimed is that given any open interval IN, give me 2 minutes, I can get an open interval IN dash with a rational endpoint. IN is contained in IN dash like this. So this is my IN dash. Okay. And IN dash has rational endpoints, R1 and R2. R1, R2 in Q. That much is okay, but how to put this condition? Length of the larger interval will be less than or equal to 1 plus epsilon times length of IN. It is not hard to achieve. That's what I wanted to prove with help of this. What I have to use is only density of Q in R. Given A and B, I can find R1 and R2 whose distance from A is less than any I want, that is epsilon dash. And R2 I am taking whose distance from B is less than epsilon double dash, where epsilon double dash I will fix later. Okay. Then finally I am getting length of A dash B dash to be equal to length of AB plus this. So this A dash B dash I am calling as IN dash. Okay. So this is always possible. Let me not try to explain too much. You can try it. So now, as previous, you can proceed. Exactly like how we proved M star E and M star of E. The same proof you can copy here you will get relation between MQ star E and M star E. Now proceed as in the previous problem. I will not write all these things. This is obvious actually. Length of IN dash and length of IN I can relate like this. That is by density of Q in R. I was just convincing myself whether it is possible or not. I would write, this is possible by using density of Q in R. Okay. Once you have that, you can proceed as in the previous problem. Now proceed. So exactly that is what we did there. M star E plus epsilon. That should be replaced by this one. MQ, M star E plus epsilon. M star E plus epsilon you start with, it is greater than or equal to summation length and so on you will get. Okay. Same proof will work. So essentially it tells that it is enough to take rational endpoint, open interval with rational endpoint. Okay. The next problem seems to be very trivial, quite easy to do. A and B are subset of R and measure of A is 0. Then measure of A union B is equal to measure of B. If you are adjoining with a set P something of no measure, then measure of the union will be same as the measure of the original. Okay. Intuitively, it is clear.
So you are not audible.
लाइट चली गई भाई, नेटवर्क गया.
Sorry, there was some internet issue. Can you hear me now?
Yes, sir.
Yes, sir.
Yes, sir.
I will share the screen soon. Anyway, I was about to stop. Yeah, this was the problem that we were trying to solve. That is quite straightforward. M star of A union B will same as M star of B, which is as per our intuition. With nothing, if you adjoin a set whose measure is 0, the total measure will be same as the original measure. Okay. Just apply the monotonicity. We have P is contained in A union B. So one-way inequality is trivially true. M star of B is less than or equal to M star of A union B. Okay. Now apply countable subadditivity. This is less than or equal to m star of A plus m star of B. Subadditivity. Be very careful while using additivity. Additivity you can use only on measurable sets. And m star of A is given to be 0, I hope. So this is equal to m star of B. So thus m star of B is less than or equal to m star of A union B is less than or equal to m star of B. Okay. And that gives m star of A union B is equal to m star of B. Quite straightforward. Okay, let me stop here. The next is very interesting. Not next, I mean the 7th one. Please try that problem. 7th and 8th, I found it interesting. 6th one is not, again, that's easy. So let me write it now itself. Give me 1 minute. Okay. M star of E is set of irrational. E is set of irrationals in 0, 1. Again, that is mere computation. So let me just do it. In no big idea is involved. And I have to prove that m star of E is equal to 1. What is m star of Q?
0.
0.
0. Q is countable. Therefore, m star of rational numbers in 0, 1 also will be 0. So the rational numbers in 0, 1 will have measure 0. Total measure is 1. Total measure of 0, 1 is 1. So we expect the irrationals in 0, 1 will have measure 1. Total measure is 1. Rational contribute nothing. Remaining should be go to irrational. So that's our guess. Okay. And that happens. Okay. So 1 is equal to m star of 0, 1. 0, 1 is interval. So outer measure is length. And this is equal to m star of E, where E is irrationals in 0, 1, union 0, 1 minus E. Now this is less than or equal to, I cannot say equal to, but less than or equal to. Even for disjoint sets, I cannot say equal to. Okay. I can say equal to only when I know they are all measurable. So this is less than or equal to m star of E plus this. And this is equal to m star of E. What about the second one? 0, 1 minus E is countable. And m star of countable set is 0. Okay. 0, 1 minus E countable. So you will get 1 less than or equal to m star of E. But everything happens inside 0, 1. Since E is contained in 0, 1, m star of E is less than or equal to 1. Clubbing these two, m star of E is equal to 1. Okay. Similarly, when you use the difference also, you should be careful. As I told here intuitively, m star of Q is 0, m star of total is 1. Therefore, m star of the remaining, we expect to be 1, I told. That is not true in general. Again, because count of additivity we don't have. M star of A1 union E2 is not equal to m star of A1 plus m star of A2. Okay. So that is what I told, we expect. Rationals have measure 0. Total measure is 1. So we expect irrational will have measure 1. And in this case, it is true. Okay. I am not using additivity anywhere, but still I am getting it. Okay, let me stop with that. Please try the next two problems, which is very interesting. Yeah.
Yes, sir. Sir, can't we use theorem that you have stated? The Lebesgue outer measure of interval is equals to its length.
That I have already used. Yeah, 1 equal to m star of 0, 1. Yes.
Yes.
That I have already used. 1 equal to m star of 0, 1.
So that is only okay.
M star of 0, 1 is length of 0, 1, and length of 0, 1 is 1.
Okay, sir. I get it.
But that will not give you the remaining thing will have measure 1. measure of A is something, and you know measure of the total, that doesn't mean you can immediately get measure of the complement. Are you able to get me?
Yes, sir. Yes, sir.
Sir, can't we
Because
use
you
the result
don't
we
know,
proved in question 5?
we don't know countable additivity. We don't know countable additivity. So simply you cannot subtract and tell. Let me repeat that point. Then I will get your question. Universal set is U and A is a subset of U. I know measure of U. I know measure of A. Immediately I cannot get measure of A complement just by subtracting. Outer
Okay, sir.
measure I am talking.
Okay, sir.
Because additivity I can use only when the sets involved are measurable. Here I am just talking about Lebesgue countermeasure, so I cannot. If it is measured, I can say. Once I know measure of a set, measure of its complement. But this is outer measure, and outer measure is not additive. Okay. Yeah, somebody was asking something in between.
Sir, can't we use the result we have proved in question 5?
What is that? Maybe, I don't know. M star of A union B is equal. Definitely. It's a sub case. Because here you have M star of rationals in 0, 1 is 0, right?
Yes, sir.
Therefore, M star of irrationals in 0, 1 will have same measure as M star of 0. Yes. The same thing, but I have once again proved it. That's it. Same thing. Whatever I have used in 5, only I am using here also. Subadditivity, etc. Okay. Or directly follows from previous. Yes, you are right. Yeah, let me stop.